Are we about to find life far from Earth? Today, we know thousands of worlds on stars other than our Sun, the so-called exoplanets. Since the appearance of the first of these, with conditions making life impossible, to the most recent, which are very similar to the Earth, the great progress made in the last 25 years leads us to think that we are getting closer and closer to the discovery of an inhabited planet. But discovering life somewhere in our galaxy will not be easy. Scientists must face major technological challenges. We are separated from other stars by vast distances, and many questions still remain unanswered. How did life start on Earth? In what kind of habitats could it appear and develop? Astonishing projects await us, such as that of the James Webb Space Telescope, which is capable of studying the atmospheres of planets in search of signs of life, and that of the ELT, a gigantic telescope that will open the door to an unknown universe. This is the time for the dream of a whole generation of astronomers to come true. Because in the end, the search for other worlds can provide a reply to the question, are we alone in the universe? In 1990, shortly before abandoning our solar system forever, the Voyager 1 space probe looked back to take a photograph from a distance of 6,000 million kilometers. Suspended on a ray of sunlight, the presence of a dim point of blue light could be made out: the Earth. Is it reasonable to think that this tiny dot is the only inhabited place in the universe?
As Carl Sagan, I think it was, said once, is if the Earth is the only place where there is life, then what a waste of space.
If life has arisen on a planet such as ours, why could it not have also appeared on other worlds?
Just a few years ago, we looked at the sky and we simply saw stars. But today, when we look at the stars, we can imagine thousands of planets orbiting them, and these planets have been forming in the same way as our own planetary system.
How big is our universe? How many stars are in it? The number of stars is very, very big. Sometimes we think that the number of grains of sand in our Earth is quite similar, but it's not. There are about 10 billion stars. It means 1,000 times more than grains of sand in our Earth.
Even if life, and even more so, intelligent life, were a cosmic rarity, the number of worlds on which it could have arisen is enormous. This was understood by the North American astronomer Frank Drake when he put forward his famous equation in 1961.
Drake equation is an attempt to measure the number of civilizations in our Milky Way capable to communicate with others.
It is unlikely that Drake's equation will ever be solved, because we are unaware of most of its variables, and each of them brings up new questions.
I think what is interesting is it depends on how many stars are in the universe and how many forms every year. How many planets they have, if they have any. Of these planets, how many are habitable? If they are habitable, do they have life already, or did it disappear? Do they have intelligent life? Is this life like ours? Will they communicate as we do? Each of these questions I mentioned, I think probably most, if not all of them, are lines of research of current astronomy. We don't want to know how many stars form in the universe, at what rate, etc. So imagine if this is a line of research in astronomy, how could we do this calculation and be sure about the result?
Since the 1970s, and with the conviction of the existence of other intelligent civilizations in our galaxy, the SETI projects have trawled the stars in search of radio signals of extraterrestrial origin.
We are designing them based on what we do on Earth. So in Earth, we communicate mostly with radio emission. And in fact, this is the best way to detect signals from humans from the outer space.
In recent decades, some hopeful signs have been found, but none of them have turned out to be a greeting from space. Were the pioneers of the SETI search too optimistic? Perhaps an event of decades before was to blame. In 1924, the astronomer Edwin Hubble had confirmed that Andromeda was not a nebula forming part of the Milky Way, but a galaxy different from ours. The universe had become infinite.
Until a century ago, everybody thought that our galaxy was the only place in the universe. Now, we know that little dots that look like stars are actually other galaxies. So yeah, we have changed a lot, and our mind cannot really understand very well the idea of infinity. We can use it mathematically, but our brain did not evolve to understand this kind of concept.
If the universe is infinite and is full of galaxies, each containing thousands of millions of stars, it seems logical to think that other intelligent civilizations like our own exist. Why then have we not yet had news from any of our galactic neighbors? This is what Enrico Fermi put forward in his famous paradox.
Enrico Fermi, an Italian physicist, posed the question of where are they? Meaning is that we have not seen or detected any signals for an alien civilization. And there are several reasons for that, possible reasons. One of them is that there aren't any other civilizations in the galaxy, so there's no way we're going to get any signals. Or we are not in the same space and time frame.
Life arose on Earth over 3,500 million years ago, but we've been giving off signals that can be detected by others for only 100 years. What are the possibilities of coinciding with another civilization in our galaxy in such a short period of time? If we add to this difficulty the vast distances that separate us from other worlds, things get complicated.
If we have a civilization that is 20,000 light years away, even if we detect a signal today, it'll take 20,000 years to get our answer to them, and then if they answer back, it will be 40,000 years. So this is not really a very productive dialogue that we could have. Now, the galaxy is at 100,000 light years in dimension, so that's a huge place. The question is, do we really know whether there's another civilization? Maybe there has been, maybe there will be, maybe there is. For the time being, we just don't know.
We do not know if we are alone or not, but we have discovered many things about the universe, which is amazing because astronomy involves a major difficulty. We cannot bring our subject of study into the laboratory. Often, we cannot even see it. How then has it been possible to accumulate so much knowledge? The key lies in observation and in making use of the opportunities that the universe itself and its physical laws offer us.
Every object in the universe emits energy in the form of electromagnetic radiation. And this depends on the temperature of the object. Light is energy. And spectroscopy is a very powerful astronomical method that allows us to split this energy using special devices and instruments into its individual portions, into its units. And the collection of those units we call spectrum.
We humans can only see part of the wavelengths, but the universe reveals its secrets to us over the whole spectrum.
The spectrum we can see with our eyes is just a very tiny part of the possible range of wavelengths emitted by different objects in the universe. So, of course, different objects emit. Some of them emit most radiation in the infrared, or in the optical spectrum, or in the UV, or in the X-ray, and that tells us what are the inner makings of stars, planets, what is the structure of galaxies and of the universe on larger scales.
Astronomy not only requires instruments capable of looking further than the naked eye, it also needs places with good conditions for observation and telescopes capable of gathering large amounts of light. The largest of them is the Gran Telescopio Canarias, which is directed by Romano Corradi.
We astronomy, we need that there are no clouds, and here on the mountains, 75% of time there are no clouds. Also, there are other two things. We have trade winds that are very good because the atmosphere is very clean, and that allows to take very sharp images of the universe. And we are in a small island which is protected against light pollution. Here what we do is to collect the light and then to get images or to analyze the light that comes from the stars. And to do that, we have different instruments. Some instruments are able to see the kind of light we can see with our eyes, and some other instruments are able to see light that our eyes are not able to see, like infrared light.
The mirrors of large telescopes allow us to gather the dim particles of light coming from the universe. Photons, which reach us after journeys of thousands or millions of years from distant stars and galaxies.
The Gran Telescopio Canarias, GTC, is the largest telescope in the world. That means that we have the largest lens. Actually, we don't use lenses in telescope, you use mirrors because it's easier to build mirrors than lenses. And here we have a mirror which is as large as 10 meters. That's very important for astronomy, because especially to look for exoplanets, where they're very close to other stars.
Down the centuries, great thinkers such as Epicurus or Giordano Bruno hazarded the opinion that there must be planets outside our solar system. It was not, however, until the 1990s that the development of technology allowed their detection.
Until 20 years ago, the 8th planet of the solar system were the only planet we knew in the entire universe. The fundamental question that everybody thinks about, the origin of life, is there life elsewhere in the universe? The first thing you need to have is a place where life can exist. We always thought, we astronomers, or at least some of us, that there should be other planets. It looked like, from a theoretical point of view, a natural byproduct of star formation.
Geneva was the setting for the first search for other worlds. In 1995, several teams were involved in the race to find a planet around another star. The first to achieve this was that of the Swiss astronomers Didier Queloz and Michel Mayor. We had just got to know 51 Pegasi B.
We just arrived at the time where the technology allowed us to give an answer, scientific answer to this very old question. So I feel myself very happy to just arrive at this good moment.
In order to discover the first exoplanet, Michel Mayor and Didier Queloz had used a method known as radial velocity, by which they could detect the slight movements of a star that were caused by the presence of a planet around it.
When we do measure the radial velocity of stars, it's all about the ability to measure very tiny variation of the velocity of a star.
This small movement can be measured because the waves of the light spectrum of the star vary owing to the Doppler effect, depending on whether the star is moving towards us or away from us.
Doppler effect is the change in frequency of the sound wave or electromagnetic wave when the objects move towards each other or away from each other. This is the effect that causes the change in the pitch of the siren of the ambulance. When it moves towards you, then it sounds like ee, and when it moves away from you, then it sounds like ugh.
On moving further away, the light spectrum of the star moves towards red, while as it approaches, it moves towards blue.
The star is going hundreds of thousands of kilometers per hour in the galaxy, but we want to measure effect at the level of meter per second in velocity. So the effect of Jupiter on the Sun is 12 meters per second, and the first generation of instruments were able to get to that precision, so we detected first big planets like Jupiter.
The pioneers in the search knew that with the technology available, they would only be able to detect giant planets such as Jupiter. To obtain a result, therefore, they would have to wait several years for these to complete their orbits. The surprise came when only a few months after starting their project, Michel Mayor and Didier Queloz announced their discovery of 51 Pegasi b, the first extrasolar planet.
When we have discovered 51 Peg, it was so unusual object, with a period of only 4.2 days and the mass about half of the mass of Jupiter. This was a complete disagreement with the theory.
Our solar system is sort of a big star in the middle, the Sun. Closest to the Sun, the small, what we call terrestrial planets. There is Mercury, there is Venus, the Earth and Mars. And then beyond, you have the bigger planet, Jupiter, Saturn, which are mostly gas planets. And then even further out, we have the so-called icy giants, Neptune and Uranus. This image of these planets with small rocky objects close to the star and larger planet, gas planet further away, has been the way people have imagined planet system would be. When we discovered the first exoplanet, this was a big surprise because they don't look like this.
The Earth is 150 million kilometers from the Sun, a measure of distance that is known as an astronomic unit. 51 Pegasi b is 150 times larger than the Earth, but orbits its star at only 0.05 astronomic units. It is so close that its year lasts just over 4 days.
Suddenly was a Jupiter not located at 5 astronomical units, 5 times further away than what you find the Earth in our solar system, but suddenly it was very close to the Sun, at an orbit even inside Mercury's orbit.
The presence of a gas giant so close to its star was so unexpected that it completely threw the scientific community.
We do not add any ideas if it's the start of a long sequence of discoveries, or it will be some unusual object.
Once the first had been found, other exoplanets with the same characteristics began to be discovered. None of them provided conditions suitable for life, but their existence proved that 51 Pegasi b was not an exceptional case.
The first planet we discovered was what we now call a hot Jupiter. This is normal because our instrumentation was more sensitive to planets which have large mass and which are close to the star. But the discovery was a surprise because we didn't expect such a massive planet to exist next to the star.
Theories were developed and further proved that planets do not stay at the place where they originally form, but they tend to migrate through the entire disk. They interact with the gas disk, but they also interact with each other. What you see in the end in a planetary system is then the product of many million, even billion years of dynamical evolution.
Science united Michel Mayor and 51 Pegasi B forever. This was the starting point in the search for an even more difficult objective: finding an inhabited planet.
After the detection of the first planet around the star 51 Peg, there was kind of a race finding new planets, all these big, giant gaseous planets. So for 10 years, that was the era of the giant planets.
While Michel Mayor was beginning the search that would lead him to discover the first exoplanet, another team was doing the same using a different technique. Hans Digg was a member of this team.
In 1994, I was still in the United States, and I was approached by a colleague, Lawrence Doyle, who proposed me an experiment to search exoplanets, which at that time I really had heard about, practically the first time about exoplanets. So we started the first observational search for exoplanets with the method of transit.
This method was based on the study of the changes in the brightness of a star.
And one doesn't see the planet itself. What one sees is the brightness of the star. If a planet orbits in front of it, it will occult a small part of the star, and the star will become slightly fainter for a few hours.
The light of a star must decrease periodically at least 3 times to be able to confirm the presence of a planet. This method, however, has a limitation, which is that when the planet passes in front of its star, it must be aligned with the Earth.
Transiting planets can only be detected if the planet is aligned in the correct way in front of the star. So the idea has been always to observe many stars at the same time, thousands of them preferentially, and hope that at least a few of them generate transit.
Hans Digg's project pioneered the search for exoplanets using the transit method, but no results were obtained. A decade after the discovery of 51 Pegasi B, only a dozen planets had been found using this method. But everything changed in 2009. The launch of the Kepler Space Telescope revolutionized the search, with hundreds of confirmed exoplanets and thousands of possible candidates. Kepler made planetary transit the most successful detection method.
It found the first systems of many extrasolar planets transiting the same star. It found many unusual things and has been really a true revolution in our understanding of extrasolar planets, amplifying enormously the variety of planet systems that we know nowadays.
A few years before the launch of the Kepler Space Telescope, 2 events led to progress in the search for other worlds.
In 2003, we installed at TISO an instrument called HARPS. It's a high-precision stable spectrograph that we use to measure the velocity of the star based on the Doppler effect. And still now, it is the instrument that is the most precise in the world to measure radial velocities of stars, and so detect small mass planets.
As Jupiter orbits around the Sun, it moves it almost 13 meters per second. HARSP could detect movements of 1 meter. Although this was still far off from the 9 centimeters per second that the Earth displaces the Sun, it opened the door to the discovery of smaller and smaller planets.
If you look in our solar system, there is nothing between planets like the Earth and planets like Uranus or Neptune, Saturn and Jupiter, the giant planets. But in all or most of the other solar systems, there are what we call super-Earths or mini-Neptunes, meaning planets that are probably mainly rocky, but with masses between 2 and 10 times the mass of the Earth. Those are not known in our solar system, but they are ubiquitous in the universe.
In 2004, a second name appeared to mark a historic moment. 2M1207b, the first extrasolar planet to be directly visible.
There is two difficulties when you want to look at planets. So planets, as you know, they are not very bright objects, okay? And the stars are very, very bright. And the other characteristics of the planets we want to look at is that they are very close to the star.
The problem is about the same as if you would want to observe a firefly, which is a small insect which produces light, that sits on the bulb of a lighthouse, and you want to observe it from a distance of about 5,000 kilometers.
If we wanted to see the firefly better, we would turn off the light. So let's turn off the star.
You need to develop specific techniques and instruments to remove the star light and let appear the image of the planet.
But this is not the only difficulty. In order to achieve such a clear image, we would need to eliminate the atmosphere of the Earth. As this is not possible, we have to use a complex technique known as adaptive optics.
Adaptive optics is a control system where you sense the optical distortions from the atmosphere that is occurring on a light wave that travels through the atmosphere by using a wavefront sensor. And this information is then fed back to a deformable mirror that corrects for these disturbances in real time. And it does that about 1,000 times a second.
The advantage of the direct image is that it allows us to obtain a great deal of information on a planet: its size, composition, orbit, temperature. The disadvantage is that we can only obtain a direct image of young planets or of those which are a long way from their star. With most of them, we will have to continue using indirect methods, such as radial velocity, which gives us the minimum mass of the planet, or the transit from which we can ascertain its size.
If we already know the mass, and we have the radius, then we can compute the mean density of these planets, and that tells us a lot whether these planets are rocky or are gaseous.
Combining transit and radial velocity is the key to getting to know the characteristics of a planet, although this is not always possible. Proxima B, the nearest exoplanet, was detected with the radial velocity method. As its orbit is not aligned with the Earth, however, we have not been able to find out its size by means of transit. Chance has a role to play in transit. With radial velocity, on the other hand, success is virtually assured, provided that the planet is not at a great distance from us. For this reason, new search projects are concentrating on the stars closest to the Sun.
In this vicinity, we see that the frequency, the occurrence rate of planets is very large. At least 50% of the stars have planets, and even small ones. So if we extrapolate a bit, it means that one star every 2 has a planet in the galaxy. There are 100 billions of stars in the galaxy, and there is at least one planet for half of them, so there are hundreds of billions of planets in the galaxy.
Not all solar systems are ideal for life as we know it. A wide diversity of stars exists that are classified mainly by their temperature. If we have to choose a good place to live, it is best to avoid the hottest and most massive stars of the universe.
They have an extremely short lifetime, so the higher mass stars are much less likely to form any planets.
This type of star only takes a few million years to consume its energy and die violently in a supernova explosion. In contrast, yellow dwarfs, such as our Sun, fuse hydrogen much more slowly over 10,000 million years, which in theory would allow life to develop.
Originally, astronomers were trying to look for exoplanets around G-type stars because our Sun is a G-type star. And of course, what you really always want to find is that an Earth around a star which is very similar to the Sun. So in principle, what we are after is a twin of ourselves.
Yellow dwarfs, such as our Sun, provide suitable conditions for the development of life. But finding a twin planet like the Earth on one of them, that is both small and just the right distance away, is for the moment a difficult task.
We have found planets close to the star, and planets relatively far away from the star, because then the light of the star is not bothering us so much as when the planet is very close. But it turns out that an Earth-like planet, which is just at the right distance from the star so that it's not too hot, neither too cold, are the most difficult to find. It's bad luck, but that's physics.
Since the first detections and the improvement of the instrumentation, we are trying to get to these small planets at a good distance from the star so liquid water could exist at the surface of the planet. That's what we call habitable in a very naive way.
We do not know how life came about, but we do know that it would have been impossible without liquid water. The search for another Earth is therefore conditioned by the presence of water within the habitable zone.
The habitable zone is a concept that is in constant redefinition and depends on different factors. How much light the star emits, what is the wavelength of this light, what is the surface gravity of the planet and its ability to retain an atmosphere, what are the components of the atmosphere, and also the abundance of water.
A planet in the habitable zone could have a temperature very different from that expected, according to whether it absorbs or reflects the radiation of the star.
A very important factor is the presence of an atmosphere. The mean surface temperature on the Earth is about 15 degrees Celsius, but it is estimated that if there was not an atmosphere, it would drop to about minus 20 degrees Celsius. This increase in temperature is produced by the greenhouse effect.
An extreme example of that is the planet Venus. Greenhouse gases have formed such a dense atmosphere that pressure is 90 times that of Earth. It is for this reason that its temperature has increased by over 500 degrees Celsius.
On the other hand, there's this albedo, which means that what fraction of the solar light is reflected by the surface of the planet. And this depends on the composition of the planet and also in which state these components are. This equilibrium between the greenhouse effect and the albedo that finally determines what the mean temperature of the surface is.
Temperature is not the only condition for a planet to have liquid water. The pressure on its surface must also be taken into account.
Planets too large probably have an important atmosphere, and if the atmosphere is too important, too massive, then the pressure at the surface will not allow the water to be liquid. If the planet is too small, it might not be massive enough to retain the atmosphere from evaporating.
This is the case of Mars, which has a very light atmosphere. Although during the day its temperature is pleasant and around 20 degrees Celsius, pressure is so light that if water existed on its surface, it would change directly from ice to vapor.
We need to find planets that have the size approximately between that of Mars and 1.5 times that of the Earth. And we believe that in that mass range, planets having the possibility of liquid water at their surface.
Thousands of millions of years ago, Mars was very similar to our planet. Perhaps it once held life, and below its surface, this life may still exist. Today, we know that some regions of the Earth that were considered sterile contain extremophilic microorganisms capable of living under extreme conditions of temperature, pressure, or acidity. It seems that life is highly adaptable.
Life is very tenacious, and even in extreme sites, we find bits of it, a few species hanging on or well adapted to those environments.
Are the limits to life much wider than we imagine? If this were the case, our possibilities of finding it would increase.
20 years ago, we didn't even know how to find one planet. Now we found thousands. Now we will be finding Earth-like planets as well. And then we can start looking really, they're habitable and there is life on them or not.
Finding a small rocky planet like the Earth is easier near its star. On the other hand, if we want to find life, it is essential for the planet to be in its habitable zone. To ensure that these two requirements are met, we must search for a type of star that is smaller and colder than our Sun, red dwarfs.
Anytime you go outside on starry nights and look at the sky, none of the stars that you are seeing is a red dwarf, because they are so faint that none of them can be seen with the naked eye, and still they outnumber the stars that you are seeing.
Red dwarfs are the most abundant stars in our galaxy. 70% of all stars in our galaxy are red dwarfs. And they're very interesting because with our techniques and with our instrumentation, we can learn more things about the planets. And we have a hope of not only detecting the planet, but also looking at what the atmosphere of those planets are made of. They are the most suitable candidates to be explored for the presence of life.
Red dwarfs also have another advantage: their longevity.
Red dwarfs burn the nuclear fuels very slowly. So when they sit on the main sequence, which is where stars steadily burn hydrogen on their cores, red dwarfs can be there for the whole of the age of the universe. Life has literally all the time in the world to develop.
In recent years, planets similar to the Earth have been found on red dwarf stars. Could any of them provide conditions suitable for life?
This kind of planets are easier to be detected. And today we have several planets in the habitable zone of this star. But we have to keep in mind that this kind of planet in the habitable zone are so close to these small stars, so maybe this is not really the better condition for life development.
Red dwarfs are much more active than our Sun and could finish off the atmosphere of a planet in a few million years without giving life time to develop. Moreover, as they are so close to each other, the gravity of the star captures the rotation of the planet so that the latter always shows the same face. This causes huge differences in temperature between the hemisphere that receives light and the one in the shade. With such a gloomy outlook, could planets develop mechanisms to favor the emergence of life? Further studies could give us the answer.
Since centuries, the human being has tried to know if we are alone in the universe or not. At the moment, we have, by first time, probably in our history, start a very challenging program that will dedicate many nights in a 4-class meter telescope to make the first survey of Earth-like planets. Who knows if maybe in some centuries or so, this survey could be used as a roadmap to go other places. Because at the end, what we are searching is similar homes like ours.
The instrument for implementing this project is Carmenes, which has been installed in the largest telescope in mainland Europe. Jesus Aceituno and his team are searching for planets like the Earth around red dwarf stars.
We select a sample of about 300 stars, and we are monitoring those stars almost every night. What is really new in Carmenes' instrument is that it observes since the very blue wavelengths until the infrared ones. And this is what converts to Carmenes in something really unique in the world.
Observation over this wide range helps us to differentiate the signal of a planet from which the activity of a star is generated. In addition, Carmenes will also allow us to find out the composition of the atmosphere of these planets.
With Carmenes, we have the technology to know what's the composition, the chemical composition of the atmosphere. What is also the second important part, just to be sure there could exist life in the surface of the planet.
The study of the components of atmospheres of distant planets is a major challenge in which we are still taking the first steps.
Right now we have discovered thousands of these planets. Now we would like to characterize them. We wouldn't like to know more than just they exist. There is a lot of experiment being built, a lot of instruments being developed to try to access these data. It's not easy. It's much easier to detect one, although it wasn't easy at all at the beginning, but now we know how to do it, so it's no longer a problem, but it's much more difficult to go now measure things at the surface of this planet. And the only thing we can really measure from so far away is the atmosphere.
Now we are in the era of detecting habitable planets around small stars. But doing that, we are preparing for the real detection of other Earths, meaning Earth-type planet around stars like the Sun. And that will come within 10, 15 years. And hopefully, we will have the new facilities to then characterize the atmosphere, because that's another challenge.
Discoveries, such as the TRAPPIST-1 system of 7 planets, which transit in front of their star every few days, provide excellent opportunities for studying atmospheres.
When there is a transit, the planet passes in between the star and the observer, so the light goes through the atmosphere of the planet before getting to your detector. So you will have superimposed to the light of the star an imprint of the chemical composition of the planet. If you can do that, you have access to traces of life.
How can we identify these traces of life? Which elements of our atmosphere must appear on other planets for us to suppose that they are inhabited?
If it were an observer looking at our planet from a very far away distance, they will be able to see the atmospheric signals that we have. We have water vapor in the atmosphere, oxygen, things like methane and CO2. The detection of these 4 elements in the same planet is something very strange, because they can coexist only if there is a system that is supporting that.
Finding planets more and more similar to the Earth and studying their atmospheres in search of biomarkers are key objectives in the missions that will be developed by the major space agencies in the forthcoming years. With its mirror of 6.5 meters, the new James Webb Space Telescope is 100 times more powerful than the Hubble telescope. There has never been a telescope of these dimensions in space, which means that what it discovers could change our concept of the universe.
We were waiting for the James Webb Telescope since years. That will be our idea machine to learn more about exoplanets. And what's the reason for that? This telescope will be the most sensitive telescope in space to capture infrared light. For the planets, we can actually do 2 things. We can image the planets, we already know, and we can measure their spectra, and we can then also derive the chemical composition of these planets.
The European Space Agency also has its own telescopes in operation, Cheops and Plato. Willy Benz is the main researcher of the Cheops telescope, with the mission of studying exoplanets that have already been discovered.
If you look for life, if you look for something, the first thing you need to know is where to look, right? You need to know where to look. And therefore you want to have a list of objects which optimize your chances, so as you think, to find what you're looking for.
2026 is a key date. On that year, the European Space Agency will launch the Plato mission. Michel Mayor and Stéphane Oudry, pioneers in the search for exoplanets, believe that Plato will be essential if we are to find a twin planet for the Earth.
On sent toute une poussée maintenant vers les planètes habitables autour des toutes petites étoiles.
Ouais, c'est clair.
Parce que c'est ce qui est accessible maintenant.
Ah oui. Moi, j'ai bien repris, en fait. C'est un peu le thème de ce que j'ai dit à Trondheim. C'est que la recherche des planètes autour d'étoiles de type solaire, des planètes habitables autour d'étoiles solaires, actuellement...
C'est Plato, hein. Jusqu'à Plato.
Voilà, avant Plato, on ne peut rien faire.
Ouais.
Plato will have 24 cameras, which will analyze the light curves of over 200,000 stars in search of planetary transits.
Plato looks at many stars at the same time, And especially it looks at bright stars, and it looks at stars at the great part of the sky, and trying to look really for planets like the Earth orbiting stars that look like the Sun.
Many of the planets that the space telescopes will discover in the forthcoming years must be confirmed from Earth using the radial velocity method.
The effect of the Earth on the Sun, changing the velocity of the Sun, is 9 centimeters per second. And that's a new step forward in the improvement.
This new step is already in motion. At the Geneva Observatory, a spectrograph 10 times more powerful than previous ones has been built. Espresso will take the detection of planets similar to the Earth to the limit.
The goal of this new project is to achieve a precision of 0.1 meter per second. And this just opens the possibility to detect this kind of planets like the Earth orbiting a star like the Sun.
This effect is so small when it's due to small planets that we have then to see changes that are really very tiny. And so we have to build dedicated instrument to be able to do that. Put the instrument in a vacuum so there is no change of temperature, of pressure, because a change of 1/100th of a degree or 1/100th of a millibar in pressure will already be induce an effect that is 10 times bigger than the effect of the Earth on the Sun. So we really have to push to the limit the technology of this spectrograph.
However, the greatest technological challenge that scientists are facing is that of Garching in Germany. It is there, at the European Southern Observatory, that a revolutionary instrument is being built, the extremely large telescope.
In few words, it's going to be the biggest highway towards the new understanding of our universe. It will give us the opportunity of discover things that today we cannot imagine.
When its construction is completed in 2024, it will be the largest telescope in the world, with a mirror 39 meters in diameter. ELT will gather up to 15 times more light than current large telescopes, and be able to distinguish objects with a resolution never previously achieved.
Think about a big beam in the soccer field. Put 10 centimeters away from it a little LED. Well, they are asking me to distinguish, to resolve the light of this LED from the light of the big focus, okay? But from 200 kilometers away.
The true potential of the ELT will be its capacity for capturing images of exoplanets on nearby stars.
Now, it won't be an image in the sense that you will not see continents and water and clouds. What we'll see is a point source. But by looking and actually seeing that point source directly, it gives us the possibility to take the light from that point source and split it up into its component rainbow colors. And if we can find evidence for molecules in the atmosphere of those planets, such as ozone and methane, then we will definitely be able to show unequivocally that life exists on those planets.
The universe that we discover with the ELT may cause in us the same astonishment that Galileo felt when he looked through his telescope for the first time.
If you look back at how our understanding of the universe has changed in the last 30 years, it's hard to imagine how much more of an understanding we'll have in another 30 years. But I think I'm confident that in that time frame, we will have characterized planets around other stars. We will have found the evidence that life actually exists around those other stars.
What we are learning in science, historically, is that when you discover something, it's opening more questions, and we are facing more surprises when anticipated. The first planets that were detected were Jupiter, but very close to the star. And we know that they cannot form there. Super-Earths don't exist in the solar system, so we had no idea that they could be so numerous. There is a huge diversity. So that's for the habitat for the development of life.
Among all this diversity and abundance of planets, shall we find another place like Earth where life has been able to arise?
Personally, I'm very favorable to the idea that life, microorganisms, exist on other planets with convenient conditions. But this is not science. The only way is to do measurements and to detect this kind of form of life.
It will not be so easy to prove 100% sure that this planet has life on it. It will be kind of hard because you want traces that are only due to life and not due to natural phenomena. And this is hard. There's a lot of things we can imagine that are also produced by natural phenomena, and we will have to be sure that to disentangle. So my feeling is we will have to have several evidence, not just one, several, because it is a big claim to make.
On our planet, chemistry evolves for thousands of millions of years to form intelligent life. Beings aware of themselves, who consider their place in the universe and look for answers.
If life is very common, then we will find it very soon, because they're everywhere. If life is rare in the universe, then it will take a long time to find, because we will need to find the right planet to look at. And if life doesn't exist anywhere in the universe, then we'll never really know, because not finding it will not be a proof that it doesn't exist.
Whether we are successful or not, the search for another Genesis beyond the limits of our solar system will have been worthwhile.
If we do believe that there is a kind of mandatory evolution towards the development of life, then it should be everywhere. But of course, there is a competition between what we call convergence. So because the laws of chemistry and physics are the same everywhere, so the same evolution should take place. But there are also the contingencies, random events that will help or destroy life or from place to place. So it's a statistical kind of big chaotic process, and the outcome will be 0 or 1. Or it's very, very hard to have life, or it's everywhere. And I choose to believe in the everywhere.